In physics, there's an important quantity called work that sort of measures how much energy a force puts into an object as the object moves around. So the definition of work is if you have an object that's moving from one place to another, and the displacement between these two locations is given by a distance x, and also there's a force acting on this object, say a constant force F, as the object moves from one place to the other, then the work done is defined to be the force times the distance, times the displacement x. And one important thing about this definition is, first of all, I guess, that the force has to be exerted in the direction of motion. So force perpendicular to the direction of motion doesn't contribute any work, it turns out. And the second caveat for this equation is that the force has to be a constant. That is, the force can't change as the object is moving from one position to the other. So with that in mind, let's work out a couple quick examples of work. So let's find the work done by a rightwards 3 Newton force on an object that moves to the right 8 meters. So the work is the force. Now the force and the displacement are in the same direction here, so they both count as positive, right? They're both going to the right. So the force is 3 newtons. A newton is a kilogram meter per second squared, but it's right, it's just some measure of force times the displacement that we're moving through, which is 8 meters in this case. And so we just multiply these. So 3 times 8, 24 Newton meters. But when you're talking about work, a Newton meter it's a unit of energy, and it's called a joule. So a joule is just a Newton times a meter, which is a kilogram meter squared per second squared. Okay. Let's look at another quick example. Let's find the work done by a leftwards 8 Newton force on an object that moves to the right 3 meters. So here we have to be a little bit careful because, right, since a force can point forwards or backwards, and a displacement might be forwards or backwards, we have to be careful about minus signs here. So our work is going to be, since it's a constant force, our work is force times displacement again. But since the displacement is to the right, if we express this displacement using a positive 3, the force is in the opposite direction, so we have to express the force as being negative. Right? So if we are moving rightwards like this, so this is our displacement, the force is in the opposite direction, and so we have to write it as negative. So that's why this minus sign is here. And then negative 8 times 3 is negative 24, and a Newton times a meter is a joule. All right. So this equation, or this definition of work, this only makes sense if the force is constant. So, what happens if the force is changing? If our object is moving from one position to another, it's possible that the force it experiences along the way could change as it moves. So how could we compute work then? Just to have an example, let's suppose that an object moves along the x-axis from x equals minus 1 over to x equals 5 while experiencing a force. And when the object is at this position x somewhere in the middle, the strength of the force is given by this function, 3x minus 2 newtons. What is the total work done by this force? So it is important in this example that the force is in line with the direction of motion. Right? Positive force is to the right, and negative force is to the left. So this definition of work we have, force times displacement, this only works if the force is constant. So what we need to do is somehow break things down so that the displacement is so small that the force doesn't have a chance to change. right? Because if the force doesn't have a chance to change, then we can use this equation because the force isn't changing. So we need to come up with a displacement that's so small that the force doesn't change. Well, this function is always changing, so to keep it from changing, we need an infinitely small displacement. So our displacement is going to be dx. Right? So at a single position here, there's an infinitely small displacement dx. So what we're going to find is the work that happens at a position x. In other words, the work that is done by the force as the object moves through the position x. So that's going to be the force at position x times the displacement to get through position x, which is dx. And then the total work is going to be, well, we need to integrate f of x dx. And we need to get from x equals minus 1 to x equals 5, so our integral had better be from 1 to 5. And now we can just compute this integral. So integral from minus 1 to 5. I guess before we do that, notice that this force is in newtons. dx itself is in meters. And so when we multiply these together, we're going to get joules, right? We're going to get a newton times a meter. That's a joule. So the force function is 3x minus 2 and times dx. And now we can just integrate. So do an antiderivative, 2/3 x squared minus 2x. We need to evaluate at minus 1 and 5 and then subtract. So let's see, put in our 5, we get 50 over 3 minus 10 minus, and then plug in our bottom bounds, 2/3 plus 2, it looks like. So 50/3 minus 10 is going to be 20/3, I guess. Minus, so here's 6/3, 8/3. So 12/3, that's 4. And this is joules. So the amount of energy that the force puts into the object as it makes its motion is 4 joules. Incidentally, this work is positive if the force is helping the motion along, and it's negative if the force is trying to prevent the motion.